Okay, uh, we are gonna try to derive the equivalent circuit for this magnetic core, and we are gonna try also to derive the voltage equations. Okay, so first we need to draw the magnetic circuit. So here we have an MMF, and so this is gonna be one of our sources. That's gonna be N1 times I1, because that's the formula for MMF. For the polarity, we use the right hand rule. So we wrap our hand and we know that the flux is going this way. So this is the polarity. And we know that our flux phi1 is going this way. Now we can see here that we are gonna get a little bit of leakage flux, uh, because in the real life the core is not perfect. So we have here a reluctance representing this leakage flux. We're going to call it RL1. Then we have the actual path that the flux is going to travel, the length, this mean path. So, and this is going to be described by one reluctance. We're going to have another loss there. And now we have another source. Sorry about that. We're gonna have another source here. That is this one, and 2 times I2. Now I already drew the polarity because, okay, the polarity is wrong. Because now the current is going this way. If we do the right hand rule, we get that this is the polarity. Okay, so we have N2, I2. And now we can see that this, because of this MMF, we have another flux leakage. So we are gonna have another reluctance here, and we are gonna call it RL2. Okay, and like that we have the magnetic circuit. Okay, the next step is finding the flux linking the coils, I'm sorry. So first we're gonna find the flux phi1, okay, and this is phi2 going this way. So we are gonna find phi1 when I2 is equals to 0. So if we draw the equivalent circuit, we're gonna still have like here N1 times I1, because it's the other source that we have put to 0. So here we have phi1, that is what we care about, and we are gonna have here the leakage reluctance produced by this coil, and we are gonna have the reluctance of the core. Now we don't have this other leakage uh, flux. We don't have it because this current is 0, so this is just a short, so we are not producing this leakage. Okay, this one RL2. Okay, now we have the circuit and we care about phi1, and we know that phi1 is the sum. If we look at this node, we know that phi1 is the sum of this flux and this flux. So we know that the flux over RL1, because they are in parallel, they have the same voltage, in this case Ni times I1. So we know that phi1 when I2 is equals to 0 is N1 times I1, that is our source, over RL1 plus Ni in 1 times I1 over RC, the reluctance of the core. So now we have our flux when I2 is equals to 0. Now we need our flux 1, phi 1, when I1 is equals to 0. Similarly, if we do the magnetic circuit, if we draw it, it's gonna be just like this one here. It's gonna be just like this one, but here we are not gonna have in 1 and I2, and we are not gonna have RL1. So now the source is into I2, and we know that the flux leakage is with respect of this one. And we know that we don't have RL one because this there is no current here, so we don't have a flux linkage here, a flux leakage, yes. Okay, and we are interested, but we're still interested just in this one, and phi 1, and phi 1 is the flux going through this resistor RC. Okay, so here we care about the flux growing through RC. Okay, so we go here. We know that they are in parallel, so the flow is growing through RC. So phi 1 when I1 is equals to 0 is N2 times I2, our source, over this reluctance, because here is phi 1, that is what we care about. So now we just put both of them together because of superposition, and we get that uh, we are gonna have these two fluxes, these two, sorry, yeah, these two fluxes, plus this one. For superposition theorem, okay. So now we have phi 1. Now we need to find phi 2, and we are gonna do the same process. We first do phi 2 when I2 is equals to 0. Uh, and it's gonna be the same process. We first draw the equivalent circuit. I'm gonna draw it again to make sure that the point is clear. We have here I1, N1 and I1 because this is where the MMF is coming from. We're gonna have the leakage flux from this. We're gonna have the reluctance of the core 2, and we are interested on phi 2. So we knew that this one phi 1, and so we know that the phi 2 is the flux going through RC. So similarly than before, we can say that the flux phi 2 when I2 is equals to 0 is just N1 times I1 over RC. We can say that because these two are in parallel, so the voltage, like analogy for voltage, the mmf through each one is the same. So the flux through this one is just this. Now we do the same. Phi 2 when I1 is equals to 0. And we have a similar story that before. Now we are interested. Now this will change something like this. And we now care about this one, phi 2. So we know that is the sum of these two. So we are going to have the, in this case, it's going to be N2 times I2 over the leakage current in the reluctance RL2 plus N2 times N2 over the reluctance of the core. And we have that in total, phi 2 is going to be this 2 plus this one. Okay. Now that we have both fluxes, we need to find the flux linking each coil. I'm sorry. So flux linkage for, let's start with the first coil N1. So it's gonna be N1 times phi 1. So now we have N1 times phi 1 is just gonna be equals to this one that we found here, all of this, and we multiply it by N1. So we have that we're gonna have N1 square here, N1 square here, this is plus, we're gonna have N1 times N2, and this is our flux linkage for for our phi 1. So now we can get our equation for the voltage. We know that the EMF, yes, is equals to N divided the dt. Okay, so if we do this, it's gonna be, it's like our flux linkage, but we are now deriving our our 5. Now if we look at this, we know that our number of turns is constant, our leakage, our L1 is constant too, and the only thing that is changing is our current in each one of these terms. So we can say that the voltage in 1 is equals to N2 squared over L1 di, then the di1 dt. Now we can have similarly the other term, N1 is constant, RC is constant, di1 dt. And now we have the last term, N1 is constant, N2 is constant, RC is constant, and we have the I2 and dt. So our flux linkage, but we are deriving our currents. That will give us our voltage equation. Now we have some terms that look interesting here. For example, this one, N2 over L1. Put it over here. Okay. we are gonna call this all I1. So this is gonna be our inductance due to the leakage in I1. So we are gonna call it primary leakage inductance. Okay. Another term that looks interesting is this one. Into oh sorry, I forgot here 1 square. Okay, this one. And this one is the inductance due to the core. So we're gonna call it magnetizing inductance. Okay, so we can write our voltage equation for the primary side as Li1, our primary leakage inductance, di dt. So you can see this is actually a voltage plus Lm di dt, di1 dt. This is another voltage. And now we have this other term, N2 times Ni1 times N2 over Rc. So it will be better if we have this in terms of our like it's something that we know, for example having like a ratio of terms, so we can get some information from that term. So what we can do is multiply the each side of the term for times in I1. So we multiply the each side for n1. So this doesn't really change the term because this is just 1. 1 times this doesn't change the value. Okay, so we can keep going. We're gonna have, we still have our initial terms, di over dt plus our magnetic axis inductance d1 dt. And now if we look at this, if we have this one times this one, we have n1 squared over rc, and we know that n1 squared over rc is lm. So here we will have lm, so just gonna write it one time so you can see it over rc, this one times this one over this one, and we're gonna have the other term that's n2 over n1, and we have di2 dt. Okay, so we did this to get lm and to have a ratio that we know. So we can factorize to make things a little bit more clean, because we have lm here and lm here, and we have a derivative here, so we can factor those two, lm the other dt, and here we are gonna have this one I1 plus N2 over N1 I2. So here we can start seeing the ratio that we care. So now we have the equation for the first voltage, for the voltage in the primary. So we can draw a equivalent circuit of this. We do the KVL. So we know that we are going to have here an I1. Okay, we have an I1 and we have an inductance. So I'm gonna draw a small inductance because this is the inductance due to the leakage, so it should be small. Okay, now we have another inductance, Lm. That is our magnetizing inductance, and we know this one is big. So I'm gonna draw a bigger inductor. Okay, and we know that this is Lm. Okay, and now here we can see these two currents. So we know that we are gonna have I2 here. Now we have I1 and I2, and I know that this current is going this way because they are adding up. So when we look at this node, we have I1 plus I2 multiplied by N2 over N1, and this is due to our coils, because we know this ratio from the transformer. So here we have our EMF that is producing this, and we have here N1. Yeah, okay. So we can draw the transformer, and now we know that this current is due to the mutual inductance. So I'm going to do it like this. We are going to have here the other EMF, and we know that here we're going to have I2. Okay, so this is the circuit for the first volt, for the voltage in the primary. Now we need to figure out what's going to be the voltage here, and so we can do something similar. So we know that now if we look at this one, at this EMF one, is Lm over dt, and we have E1. Yeah, we have I1 going here. We have I2. So we have N2 and 1 and I2. Okay, and this is the same as having N1 squared, because remember that Lm is Ni squared over Rc times Tt I1 plus N2 over I1 I2. So it's just to remember that Lm is Ni1 over I2. So we now are going to try the same for this side. So we know that E2 is I1 over N1 times M2. And we know this for the ratio of the transformer, for the equation of ideal transformer. So we know that this equals to all of this, and N1, all of this, times N2 over N1. So when we do this, N2 over N1 times this, N2 squared over Rc, derivative of I1 plus N2 over Ni1, N2, Now we can do some manipulations to try to get information that we care. Now we this is n2 over I1. Okay. So we should try to put this n2 over I1 uh, over, yes, instead of multiplying it to I2, we needed to multiply I1. So we can have the I2 alone and we can look at the circuit, how it's gonna look like. So we can do some manipulation and we are gonna have that. Here we have N2, this is I1 square, okay? So N2 times I1, because we just take one of this, and we divide this by RC, this one here. And we put the rest inside the derivative. So we are going to have I1. Okay, here we just cancel I and 1. This one and this one. So we have this. And we still have I1 plus N2 over N1 times I2. Okay. Now we are gonna try and do the same thing. We are gonna try to still, as I say, we are trying to get the ratio over this one. So we are gonna multiply both sides by n2. Again, this does not change the term because we are just multiplying by 1. But if we do this, we have, remember this is e2, n2 squared over rc. So if you look at this, n2 squared over rc is our magnetizing. So we are starting to get information that we care about. N2, and this part doesn't change. And now what we need to do, sorry, we keep our magnetizing inductance here. And now if we factorize, if we multiply this, we are gonna have n1 over n2 I2, n1 over n2 I1, I'm sorry. And when we multiply by this, we're gonna have that this one and one, and this one and one is gonna cancel, and this and 2 over this 2 is gonna cancel. I say cancel, but I mean when you multiply this 2, you just get 1, so you're gonna have 1 I2. And now we have an equation for our EMF for the secondary side, where we have our magnetizing inductance times this expression. So here we have, and now we are gonna have to find the flux linkage for our second coil. So we have N2 and Phi2. And if we do all the math, we're gonna find that it's gonna be the same that, oh well, we actually already did the math. to find the flux 2. So we to find the flux linkage, we just multiply by n2. If you remember, we did this at the very beginning here. So we multiply all of this by n2. So we are gonna have n2 squared, n2 squared, n2 times n1. And similarly, we're gonna have that our voltage equation for the secondary is gonna be n2 divided 2 over dt. And we're gonna do the same analogy. We're gonna see that this is up here is our flux linkage, but we're dividing our flux, and in our flux, the only thing that changes is our currents, because the number of turns do not change, our leakage flux does not change, so and our flux or reluctance in our core does not change. So when we do the voltage equation for 2, it's going to be n2 squared over RL2 this side, deriving our current, plus n2 squared over our core, and we do the same current, and we have n2 1 over RC, and this time we have here I1. So it's very similar to the last one. Now we can factorize a little bit. So we have B2. So again, so if we look at this one, this is just our, if we look at this one, this is just our leakage inductance to 2I2. So we're gonna call it Li2. That is multiplying the IDT. So this is one of our voltages, plus we have here our magnetizing, n2 squared over RC dt, multiplying, now is n2 squared because I'm factorizing with this, so I'm taking this n2, putting it in here, I'm taking the RC. So to able to factorize n2, I need to multiply n times n2 and n2 up here and n2 here to factorize this into a square. The RC is here, so we can just take it here. So we're gonna have n1, okay, over n2. Here we have I1 plus I2. Now, if you look at this term, this term looks exactly as this term here that we figured out for E2. So basically, our voltage in the secondary is gonna be our leakage inductance times di2 dt times plus E2. And like this, we have both. Now we have both voltage equations. We have V1. I'm just gonna write it again to have it right here. V1 we have is our leakage inductance due to I1 times di1 dt plus our magnetizing inductance times di1 plus n2 over n1 I2. Okay, so here I'm gonna draw the circuit based on these two equations. Let me make it a little bit smaller. Okay, so for the primary, no much changes. We know that we are gonna have our I1. We have our small leakage inductance due to I1. We have our magnetizing inductance. We know we have our I2 that when they go through LM, they sum up. So this is I2 over I1. We know we have our coil that is producing the EMF. Okay, then we know that this coil is N1. Now this is a transformer so we draw the transformer symbol. We know we are gonna have our other coil with a number of turns N2, and we now figure out that this is our voltage equation. So we know that here this is our I2, but we now know that we have here our leakage inductance due to I2. This is our EMF in the secondary. So here we have our B2, and here we have our B1. Now, here we are only accounting by the leakage flux losses, but we could add another resistor here, R2, and here another resistor, R1, to count for our copper losses, because in the real world we're gonna lose a little bit due to the resistance of the copper that the coils are made of. So like this, we have derived our equivalent circuit of our transformer, taking into account our copper losses, our leakage, flux losses due to the primary, our leakage flux losses due to the secondary, and we have both our voltage equations. I hope this helps. That's it.